Good morning, everyone, on the Friday of the conference. So I will be talking about modules. And who here has heard or seen or tried modules as a feature out? Okay. But let's start with more of a overview introduction, because we programmers very rarely write code by ourselves. Last night, Marshall was talking about the standard library, but there are, of course, many other libraries than the standard library. So in many other programming languages, eventually, or from the very start, there was a way to, after some downloading of some packages and having some build configuration done, have a very nice way of just saying import some name, and then I will get the symbols in that package or module or however it is called in that language. However, in C and in C++, we had a very different approach, which was the preprocessor and headers and the linker. So in case I wanted to use a third-party library, of course, I had to include the files and then set up linker flags, etc. Okay, of course, linker flags are taken care of by CMake and various other tools. But there are some tangible issues with the preprocessor which led to the inception of the modules feature. So let's go on with a generic overview first. So let's say I want to use some new symbol. Here's some dummy code. I want to use that symbol. And my IDE has some auto-completion, which is not quite the best because it's only giving me a macro. But of course, it knows I'm using Clang, so it will suggest to me the header and then take care of including it for me. Now the syntax highlight shows that it resolved it as the class. But the big question is, did I break something by including that header? Because I might as well could have. There was a talk about ABI problems. There's not just ABI problems, there's also problems during compilation. So we will talk about basically the most fundamental issues with the current compilation model, then mostly about modules, and there will be the main part of the talk is the automatic modularization, which I've worked on. So when we write, C++ does something which is called separate translation. Hopefully we all know it, that the compiler is invoked by some driver on a single source file, always a single source file, no matter how many files you have in your project. We run the preprocessor, evaluate the directives, we find some other files which are the includes. We also preprocess them transitively until there are no more preprocessor directives found. Then we have something called the translation unit, or in this context, input buffer, which is a single textual stream on which we do all the semantic analysis, template instantiation, code generation. And of course, once all of this is done for all your files, the linker will take care of creating a binary for you. Now, when people write code, they will want, there are different phases on what we want from a programming language, from a tooling. And I've got a comment about the initial proposal for this talk that it is a bit two-phased. I will keep that direction. There are two phases. So on the left-hand side, there are metrics or properties of a software project. That is the property of the code that you write, good code, whatever that means for you and your team. Readability, writability, performance, not having undefined behavior, etc. And on the right-hand side, there is the one that we don't expect from our own code, but rather the environment, the tooling, static analysis, coverage, code comprehension. And on the tooling side, there's, of course, the compiler and build chains, which all of these things can be hurt by the current model of C++ compilation. But first, let's focus on the left-hand side mostly, not the performance concerns. So because we run separate compilation and there's no knowledge about other translation units, of course, the most simple thing we can mess up is that we create two parts of our project. one of which should emit the build date, which is generated by the compiler. And we have some other library which we purchased for money, and it has a license date on it, and the function which gives it to us. These two files of the project are perfectly valid, as long as you compile them separately, and they are two different objects, maybe two different libraries. However, software evolves. So eventually someone will want to create a help output which will both tell you when you built the program and when you licensed it. So they will do something like this, include both headers, of course, because you need the headers to propagate the type information about this license start date function. And now everything will break because you are redefining a macro. Okay, every compiler of today will give you at least a warning about this, hopefully. But there's not just token leak, there's also something called name leak, which is not on the preprocessor, but now we are inside C++. So let's imagine we have two headers defining two different classes. There's some detailed stuff in the header. As long as we don't depend anywhere in our program on both files, everything will be fine. The moment someone will depend on both headers, hopefully the compiler will notice and give you an error about violating ODR on the detail function, hopefully. Now, because of all these issues, various people and organizations came up with coding guidelines, rules of thumb. For example, this issue is more problematic when it is not this simple, when you accidentally pollute your namespaces and mess up ADL, etc. Many companies, for example, Google also have their own style guide, but there's like core guidelines, CERT, etc. So here's this imaginary code, which, okay, so we forward declare because we don't want the definition to be there, because we don't need it, we don't want to instantiate it, we only need to set a pointer on the thing. So here's this code, a test, because we don't know the inheritance between B and D, it will perfectly work as returning 1. However, the moment the code evolves, someone will include the real header which defines these types. We will see the inheritance, and the test will break. So the people at Google said, no, you should never forward declare. This is yet another rule of thumb which may or may not be enforced by tools, by code review, etc. But another issue that comes up when you write your code is that once you put your symbol into the input buffer, it's there forever. You cannot take it out. So let's say I'm writing my code, I want to use something from the stud namespace, and my IDE will show me a bunch of symbols, including red, black, 3. Of course, that's the implementation detail for stud map. So what you could do to prevent this, in some cases, in your libraries, you could do like static symbols, anonymous namespace. However, this internal linkage is not a solution for templates. So let's imagine there's this template. I don't want people to call the foo function, but for some reason it's part of the class. I cannot really put this into the static namespace because this is some user-facing type that I want to use. And seeing something like this as a code maintainer, more or less, makes me think of two things. Is that expression x of int default constructed .foo a valid naming? And can I actually call that function? Well, of course, x of int foo is a valid naming. There's nothing sphinx here, etc. X is defined, foo is defined. Of course, you will call it with some concrete integer. But when you try to call it, the compiler will tell you that you cannot call a private function, which is, of course, what we expect. However, there has been some, before the reflection, there has been some fancy abuse of the standard that, yeah, maybe you can call that. There are ways in the cited paper with some unevaluated context template magic. So let's see an example which is more live in the real world. Rules of thumb have a problem that there is no enforcement on it. So here's an idea. People came up with stuff like detail namespace. Of course, the standard says about whatever number of underscores in the names you shouldn't use, but there is nothing preventing you from using that. Here's an example. Someone uses their favorite library to check in some arguments, whether or not there are CPP files in it. And because in the documentation, in my IDE, I saw that there's that type which will give me a result, I can just do this, and it will compile, it will work. It will work until I update my library, because this is a detail namespace. Of course, the Boost developers can break it, and I will be at fault. However, at the point of writing this, perhaps no one tells me that I'm at fault. So the thing is that the issue is that you use the detail namespace. Of course, you could have a code review pass in the CI loop that grabs on using detail or whatever. However, both compiler errors and any linters or analysis tools only go so long. Hopefully, all of us have seen that people will always try to go further. So some of these issues with the names leaking out and that led to the inception of modules. However, there's also a problem with the compilation model, which I have experienced daily when it comes to tooling. Because there was this slide at the beginning, okay? So I am writing my code. I only have to do this whole thing once per rebuild, right? No. Of course, the compiler does this. But if you have anything else in your environment, such as a static analyzer that rechecks your code, some sort of code comprehension tool or indexing, air tags, you complete me, etc., formatting tools, some refactoring because you work on a code that's generated every time, metrics calculations. I mean, I could talk until midnight about these tools. They will all do at least the parsing. They won't do code generation. They will do something else down here, but they will do the parsing. So a bit of a two-face is that I want to write good code, but I also don't want to spend all my life waiting for the compiler. And it's the motivation behind the original question behind this research was more of a personal story. I was working on Code Compass, which is a code comprehension tool for C projects written for C++ projects written in C++. Mostly all translation units depend on these four, actually maybe 5 or 6 libraries. Now, if you think about it, either of them alone would be enough for kicking you out, but all 4 of them. Now, I was having a particular system, 24 threads, 40, 50 gigs of RAM, and I was working in a single translation unit trying to put together an algorithm, and an incremental rebuild of that translation unit was 6 whole minutes, which is insane. And after a few days, I gave up and I went like, okay, this needs to be better. So I realized that particular system was running on a hard drive because 60 gigs of RAM was not needed. I mounted everything into memory. I was able to halve the time required. Then I saw we are depending on parts of libraries which are doing template instantiations which are not that much needed or could be refactored out. I went down to 1.5 minutes. But I couldn't go any lower than that. And it's a machine from 2012, but the thing is, compared to many other languages, the compilation model itself gives us a big overhead on stuff. And, well, it was researched many times before. The issue is that due to separate translations, the compilers don't know about each other. They might not run on the same machine even if you have a distributed system. And every compilation has to read from some sort of storage your included files. Previous research has shown that in many projects, a very significant chunk of the input buffer is basically copy-paste. So here's an example from the doctoral dissertation of another student of my supervisor. This is only about the preprocessor, but the finding is that if they put the code into a Unity build, the lines the preprocessor had to load went down by 90%. Now, these projects are perhaps mostly C. In C++, we have another armory of big guns. I haven't found any research that actually measured the cost of the template instantiation, but knowing C++, we can imagine it's even worse than this. And the big problem about template instantiation is something called the weak reference. Assuming you adhere to the one definition rule at linking, the linker will see that you have 75 million instantiations of vector, int, pushback, whatever. It will keep the first one and don't care about the rest. So we did all this work, assuming you don't link the same object into multiple binaries, for no use at all. So about the performance, there are some tools like boosting the build performance, but they are mostly workarounds on this. Compiler developers came up with the idea of precompiled headers, which is about just saving out all the template instantiations and the compiler representation to be able to reuse them later. This is nothing in the standard. This is a pure optimization inside the compiler. Other people at other companies in other compilers came up with an idea of automatically creating this precompiled header for each translation unit. So if you only change the body of your CPP file, then none of the headers need to be parsed again. And perhaps, just perhaps, modules would also show some solution to the performance. We will see. So modules, hopefully it's a very nice feature. Now, Clang has a more or less fully working implementation on the thing, which uses precompiled header representation inside the binary. So let's compare precompiled headers with modules. Now, precompiled headers is just basically a different form of a compilation output. You don't generate an object file, you generate a precompiled header. So you have like one compilation, then that header is used by the other one, then you have a precompiled header which contains both headers' content. Then you have a main file, an input buffer, and then you compile it. So this is a line. You can break this line anywhere, but for each compilation, you could have at most one precompiled header, so it's always a line. Now, compared to that with modules, you have some file that describes your module. You create some representation of it. I think the talks on the mailing lists refer to this as the binary module interface. Deep down inside Clang currently, it's the representation of is a precompiled header just with more metadata, but that's a Clang internal thing. So this is 2019, May, right? Modules was originally formally proposed in 2004. That's a long time. But luckily, in Kona, people decided that it's officially part of the CPP 20 feature set. Hopefully, compilers will live up to it. Now, going away from separate compilation, but still keeping it, we try to go away from this header mechanics and use a logical packaging system. Now, but to not change fundamentally how C++ works, one module is still one or a group of translation units with all its benefits and drawbacks. Now, you have this fancy new keyword import, and then an identifier which will direct the compiler to import module M for you. We will see how it works. And more or less, the preprocessor now no longer has effect between these translations. So we hopefully solved some of those leak issues. But unlike some other languages, in C++, the module's name does not form a part of the symbol's fully qualified name. So even if you say import container, import vector, it will still be std vector of t, not container : vector. And well, proposal or the current draft, I hope the wording is lax enough to allow some compiler optimizations. This is a foreshadowing that maybe the performance problems are not truly solved yet. So For the people who hasn't seen modules live, well, I won't do a live demo, but here's an example. So you declare the name of the module at the top of the file, export module identifier. This will say this file is the main file of my module. And then you just write C++ code as you would have any other way. You have some functions that return stuff. And then in the client code, you say import module. You have some variables. OK, so what can we do? We can, of course, call 4 or 6, hopefully. So you have this new feature called visibility with the export keyword, recycled keyword. So you can distinguish between two symbols, whether or not they are exported. And if I try to call these functions from the client, what I will get is a compiler error which says no function named 4 in the current scope. Remember the template? The template class said, or any class says, that you cannot call the private method, but it will leak to you the information that that private method is there. Now the module says, no, there is no 4, there never was. It should behave as if no one defined it function. But of course, inside the module, 4 is a defined function, so 6 will return 6, and if I remove that line, the compilation will go away. So, for the ifconst guys, no way, okay? So, because mostly I work with Clang is westconst, so I will stick to that. So I talked about loading, importing a module. This is a very nice screenshot from the current draft. So when you encounter an import declaration, you will find the translation unit for the module and load it, whatever load means. The standard doesn't say it, it's an implementation detail. And of course, if that module depends on some other modules, you will transitively load everything. So it's sort of the same as we had with hashmark includes, right? However, included files are sort of easy. You just send the include flags, and then the file is there. I load it. If it isn't there, I throw an error. But modules, the people behind compilers and build systems are still in a bit of a debate. So I have prepared 2 animations on how modules should work on the build system. I will foreshadow, I hope this, what I call preventive, will win. So let's imagine we have a project with 3 source files. M is the module. CPPM is just a decoration that it is a module file. It's just another CPP code. So I use some high-level build abstraction tool like CMake, which will generate build configuration for the person's favorite build driver. In this case, Ninja. It could be Make, Xcode, anything. Ninja will have in its database some compiler invocations, still 1 for each compilation. And hopefully the build system will know that my normal translation units depend on the module. So at first it will compile the module. In the current implementation of Clang, the compilation of a module has 2 outputs. We have this PCM, which is the binary module representation of the compiler AST. And we have the generated code object file, which is created as if it was a normal translation unit. And now that I have the module compiled, I can call in whatever order or parallelism you wish the compilation for the normal files, which will, of course, realize the module is needed, load it, output the object, compile the other one, load the module, output the object, and then we link it all together into some sort of a binary. Now, there's another approach people suggested that maybe we should do the whole thing on demand. So let's say we know that my project is 2 translation units, X and Y. Maybe the module is from some other part of the project. So I will once again create the build. There are the compiler invocations. And first I start building one of the translation units, in this case X. Let's go lexicographical order. Now when X is compiling, the compiler will see the statement import M and will go, hey, I don't know what module M is. Where is it? Give it to me. So in this on-demand or inline approach, it's debated, but it will call back to the build driver, to the build configurator, fork another copy of itself. It's just a debate on mailing lists. But basically, the compiler will go back. Hey, you are the build abstractor. You told me to compile this file, but I need a module M. Where is it? And hopefully, the system will know how to create module M. So now it finds the module, create a compilation, a separate compilation for the module file, which, as we said earlier, gets compiled. Now that compiler exists, we go back to our first compiler invoked, which will load the module, go on with compilation as normally, output the object file, and then we do the same with the other translation unit and link it all together. So eventually, this is a bit of a demand. I think it was the GCC people who suggested the callback system. Personally, I would want the preemptive one. We will see. This is not concern of the standard implementers and the library guys. Whatever build system you want to support, you will write your project for it. I think currently CMake is not yet supporting modules. I have made a pseudo implementation which kind of got stuck in a very important step. Ninja is getting features that allows for dynamic dependencies handling with modules. Build 2 has been having module support for a long time.
So CMake recently added support for GCC modules.
Ah, okay. So the comment was that CMake now added support. Back in like March, there was still not. Okay, so now that it's officially a feature, people are catching up. So what has modules ever done for us? What did it fix? Now, we solved the token leak with not having the preprocessor effect between compilations. We have now a way, sort of, to hide true detail, which has no need for like detail namespaces and such. We can get better explained interfaces. So some of my colleagues work in static analysis, and one big hope is that together with contracts, modules will be a very good way to express an interface which the compiler cannot see. So let's imagine you have some secret library, which you as a client in the business sense have no access to because you get it as an object file. So currently what you could do is just type out stuff into the header, which is English or even not English, and then maybe you keep it, maybe not. You could have put a no except false there, but anyways. So this is in the library, but what users and their tools see is just this, which is really not enough to test the behavior if someone messes up. But together with contracts, now we could say there's a precondition, that's the contract part, and we could say with expert that this is a function in this library you can use as an entry point without any details or 15 underscores in infixing the name. But we also solved a problem on which header to use. Like, I could use boost variant with including 7 different files. We just pushed it over to the build system people. So did we fix all those problems that I have been talking about before? That is the big question. And it turns out that we did not. Now, there are some new issues with the modules. Now, there's an increased burden on the build system, both to support it and then to do it in a way that it doesn't break. Library vendors now need to make an extra step to, well, describe how their library fits into a module. It's not enough that you download this library, put it into whatever include root you are using, and then just include this file and everything will be dandy. And there are some new ways to shoot yourself with modules. This is not particularly my finding, there's the citation here, but but this is very interesting. So because modules introduce new concepts into the language, we have now an even bigger vocabulary of properties of a symbol we need to well, not actively be in the knowledge of, because once people start using modules, this will be muscle memory, just like perhaps ODI, not doing ODI violations will be muscle memory. But here's an interesting example. We have a module M, which has an owned integer wrapper, and we have a factory method for that, which just gives me an owned 0. Now, there are two new concepts, visibility and reachability. So the weird thing about this code is that struct S is not part of the module's visible or nameable interface. But it is reachable, which is a whole new concept in the standard. We will see what's the difference. So let's say someone wants to use this owned integer struct because pure integers on the stack is not cutting it for them. But they say, getting an owned 0 is not good, I want a 1. So they write this, and okay, so in pre-module C++ world, this will be pretty fine. Like you just, we saw that there's a member initializer constructor, so you just create a 1. But what the compiler will tell you is the same as in the example with the for function. It will say that there's no, so it will realize this is a variable declaration, and it will tell you that there is no type named S in the current scope. Because it's not exported, it's not visible, you cannot name it. However, there's a function who can and will return this variable for you, and you can use decl type, auto, whatever you wish, to actually create this variable, and it will work. But then, because this is a struct which has members, and you should be able, like you wanted a 1, now this is a 0, so what you will do? Set the variable to 1, and this will also work. It's not an issue with the build system or the standard itself. It's more of a thing that people can mess up, and it's more of a thing that IDE developers, code comprehension tool developers will have to keep in mind. You could do this with anonymous types with return auto and stuff in C++ 14 already. But the thing is that S is reachable because it's part of a semantic rule set which leaks out of the module. So there are things you cannot name but are still there. Yes?
So do you view this as a problem?
The question is if whether or not this is a problem. So this is something you can truly abuse. There are some more examples on Vector of Boo's blog, which shows that perhaps subtly removing the export keyword on the top will break your overloads and stuff. This is something you can mess up. This is something you will have to practice to not mess up, but it's not necessarily a problem. It's just something IDE developers, code comprehension tool developers, and programmers in C++ will just first have to learn. Gaspar was first.
Is there a difference between returning S by reference and S by value in reachability?
I don't think so. The question is that perhaps returning a reference to S will make a difference here. I went through the current draft, and I don't think so.
Okay. Second question.
Yes?
I'm really surprised by the S.m thing.
Gaspar is surprised by the S.m thing, and he's right in that. Now, the thing is that originally there was an implementation in Clang, a very early one with modules before it was even part of the draft, which allowed you to partially export symbols from inside the class. Now, while it's really, really funny, it just broke everything. You could have had two translation units in which the same class had different members and different sizes, and then it became a big mess when you had inheritance. So the people who are behind modules have decided that inside the class, you can no longer partially, like you cannot export only a few members or only a few methods. And
These things are orthogonal, right? Like you could say you could make this class, but you can't actually name any of the members if you don't export it explicitly, right? Like the compiler should see the entire class.
Yes, the compiler should see the class, but I think it's more of a safeguard that you cannot, like if you don't want inside the class people to access your members, there's a mode for that. It's called private. And you cannot, so in case you have another module which also has a struct S, a different struct S, and also has a factory method which perhaps is an overload here, you cannot import the two modules into the same translation unit because the new wording for ODR will say that struct S as a type, because the module name is not part of its name, is reachable. So you are now in violation of ODR. Let's go.
I'm not sure. Is that the case even with the strong module ownership model? Where the module that something is in is part of the AEI of the type.
I have read a paper about the strong module ownership model, but I'm not sure about that.
So my actual question: would you personally have preferred that this be an error? That this be an error, and that you need to export S if you want to return it from or use it in an interface that's exported?
So whether or not I prefer for it to be an error, so the compiler should check transitively that if something is reachable from a visible symbol, then no, you have to make it visible too. Well, it would make make more expressive code, because you can now type out the types, but you can, for example, create aliases on the decal type. Due to the ability that we can still do this in C++14 with return decal type auto, it's the same behavior. I have no hard feelings about either way. The fact that you can access the members is a bit weird, but considering that decal type's lowercase s is unique, compilers and IDEs hopefully will be easy about showing this. In case the struct is inside a private part of the module, then you don't need you don't have the ability to access it. There was someone in the back.
So far this makes perfect sense by analogy to lambdas. I can't name the type, but I can get its members, such as operator paren. You know, in this case, I can get it .m, I can get it a member operator plus, I can get it the copy constructor. These are useful things. I like this. But I wonder, so I can't, as a user, I can't name the type, but the compiler still knows what namespace it belongs to for ADL
Yes.
and what associated
Yes.
it has and all that. What about its ADL friends? If it has an ADL swap, like, is it going to find that?
The question, what about ADL? So the compiler, so you cannot write down the type as S. So S as a symbol is not defined, but you can do something like using uppercase S equals decal type lowercase s, in which case the name will be available to you. In terms of ADL and lookup, there's a new concept apart lowercase, like language, not C++ concept, but English concept. There's a new concept apart from point of instantiation, which is called the initialization context, which definition is there to solve the issues. Everything that is semantically available is called necessarily reachable. And there can be things, implementation specific, that might also be reachable, but you shouldn't rely on them. And I think the people behind modules put enough work into trying to make it all work. But we will see.
If I have a friend void swap sref, declare it in the body of S, and S is not exported, and the friend void swap is not exported, and I swap two S's does it not see that?
Because S is reachable due to being exported from, so inside the module it will work. Outside the module, S is leaking out because of reachability, and hopefully it will work. I haven't tried it this fancily. Yes?
I had to think about the whole, you can access the members if
Yes.
S leaks. It would be utter insanity if that weren't the case, because you couldn't access the special member functions either, which means you couldn't even copy it. And that might actually mean that you're not able to even write the first line because you're implicitly using the copy constructor in your new translation.
Yes, yes.
So,
Yes, members need to be accessed so that the stack of the function which is using the not visible symbol should have written not visible there, but it looks good with export and not export. So the stack needs to make sense. And here is the previous comment about a previous implementation in Clang which somehow allowed for partially exporting things, and it just messed everything up.
Just to clarify, guaranteed copyism from C++17 should mean you no longer need another copy or remove constructor for that to work.
Yeah, for that part.
That is correct. The analogy holds, yes.
That particular line.
Export your destructors.
Yeah.
Yeah. So sorry. We still have a few slides. So yes.
Yeah. So like I have a comment on the member thing. I hope that somewhere in the future we could get a language level input this model because it's actually possible. And correct the members.
Yes. Hopefully this will also allow better idioms which we learned before. So new ways to shoot yourself in the foot, as we've seen in the debate. But there are also some new implementation-defined behavior, particularly about what's reachable but not necessarily. So what is not necessarily reachable but still reachable? Everything which is visible is reachable. Everything which is necessarily reachable is reachable. You can look it up. It's sets that contain themselves, so it's not that hard. And of course, there are performance concerns. So in some case of the world, there is something that module does not solve yet, and hopefully will be up for the compiler guys. Small example, let's imagine you are using std_vector and are just returning 0 in a very fancy way. I know the compiler could const expr optimize it out with const expr, but whatever. Let's just imagine this is a runtime check on the vector size, imaginary module containers. And if I compile this and check the output of the normal C++ file itself, then I will see that there's a definition of weak reference to vector size, basically. So it's in line with the preprocessory behavior. Template instantiations are still part of the compilation that are using the templates. Hopefully there will be optimizations around that which trickle down from the wording of the standard and ODR. So we killed the preprocessor, more or less, in so many cases. However, there's a new guy in town who perhaps is even worse. So another small personal story about a thing called AST reader, AST importer in Clang. A few of my colleagues are working on cross-translation unit analysis. You can look it up. Basically, if I dump LLVM as precompiled headers, it will be like around 60 gigs. And what some of my colleagues in the Clang analyzer are doing is that they just load these things. More or less, we could draw an analogy with modules. You are loading translation units together. And they have found some very weird stuff that to analyze a code, you need a lot of translation units loaded. It's a lot of memory usage. Of course, there are duplications in symbols between the translation units. So they had just opted for an arbitrary cap so that we can still run the analysis on a 32 gigabyte RAM machine. So there's perhaps a different performance concerns with modules. However, there's something more of a problem. Yes?
But it's actually, like, it's not the case with modules because it's with units, it's quadratic size.
Sorry?
Like, each of these translation units includes several modules multiple times, so it's not
Yes.
two numbers with modules.
Yes, it's a dump from the current pre-modules word, but there's a fear that this analogy is maybe with smaller numbers, but it's still could pose an issue. But there's one very, very big problem, and it's this. Whole lot of zeros, let's write it this way. So million of English word and million of other parts of Europe won't mess up. So what's this? Anyone has an idea? Sorry? It's a big number, yes, but what's the measure? It's lines of code. I know lines of code is not a very accurate measure of stuff due to template instantiations. A few weeks ago, I asked on Slack, like, what would you say, how much CPP code is out there in the world? People said, I think it's billion in English, whatever, 10 to the power of 11. This is all the code we use day to day, and it's not using modules at all. So here comes the other part, automatic modularization. So people are generally lazy. So why couldn't we just use a tool to upgrade an existing project to modules and then be happy and go making new stuff instead of refactoring our code? Now, this is more of a foreshadowing of the final outcome, but let's go through what I did more or less in the past bit less than a year. So the goal is that I have some existing project and I want to put it into using the module system. What I have about this existing project is, of course, the source code. I can check it out. I can build it. I can create some configuration metadata from the build, you know, like compilation commands, etc. I have some initial mapping. I trust the developers. If you put your file into src/whatever, then it should belong into the whatever module. This is easy to generate. It's just a shell script. Of course, it's not a sensible module, but it's an initial input. But I know nothing about what your project does. So what I wanted to make is kind of a tool you can give any project which you are legally authorized to give me, and then it just creates the modules for you. And of course, the output should be some sort of a module mapping. So original source files to modules, which is sensible. Now, greedy algorithms sometimes don't really create sensible outputs, so I moved the goalpost a bit, and my wish was so that it compiles. Okay, just get it to compile and work, hopefully with the same behavior as in the conventional C++, the pre-modules C++ world. So what I did is do some fact extraction from the code. So I actually run a different front end than a compiler, create a dependency graph. These are very standard stuff in analysis and code comprehension. Then there's this abstract graph which creates a flow. Colors are modules, calligraphic letters are modules, other letters are files. The one and the infinite are just, you know, flow algorithms, the capacity of the edge. We will see example of it on a project later. And once I have this flow graph, I just use cuts, well-known and well-discussed mathematical algorithms. Then I have to do some more magic on the code due to ODR and ownership of symbols, and then fix the whole thing so it's conforming to the standard. And the result is kind of like a Unity build for some automatically synthesized components. My aim was to not touch your code at all. Yes?
Can you just explain for a little more?
We will get into the steps, step by step. So the whole thing is using Clang because my team at work is very familiar with Clang. I wrote the driver, the infrastructure, and yes?
I want to understand this better. Like, do you ingest the whole project and then you spit out a bunch of things and you don't care for what was already grouped in the files previously? Or
I care about it initially and then I reorganize them. We will go through the steps.
Okay, so it's basically you're treating every function as a separate thing.
Every file. My granularity is on the file level.
Okay, that's what I was looking for.
Yes, I'm on the file level. I don't touch the layout of your files. The story behind that is that many researcher friends who worked with refactoring have learned, this is not a proven and published research, but it's a hush-hush word, that moving a function from one file to the other is a can be a geopolitical issue. Because if you move a file from one folder to another, you might have moved responsibility from, I don't know, Germany to South Africa in the company. So I didn't want to touch where your files are. So originally, it is in Python. I find some very basic stuff. I dump out your includes, your symbol usage. Now, because I'm joining files together, I'm doing something like a Unity build, but just not for the whole project. There are some cases in which Unity build breaks, such as, local types of, yes?
What is Unity build?
Unity build, sorry, yes, I forgot to say. Unity build is when you just dump all your translation units into a single file and you compile it as such. Maybe not your entire project, but per build. So you don't have to do the pre-processing and the templates multiple times. So if you have a local type def in each translation unit, which is different between them, now it will break if I copy-paste the translation units together. Macro defines could beat it out. I put it into parens because I didn't actually, it wasn't much of a problem in modern C++ code, so I didn't actually implement anything around it, but we could. And there are forward declarations in many codes which pose a problem, and we will see. You have a question?
No.
Okay. So what about forward declarations in modules? This might be an older version of the draft. It might be some papers not merged into my thought process. Imagine we have two modules, one of which is forward declaring a four-wheel driven vehicle. And there's a pointer. Maybe this does not need the definition at all because it's just putting it into a global vector or something. And there's another module who actually define this class and export it. Now, in this very case, the two four-wheel driven cars are two different things. There's no connection between them, but we want to have a connection between them. So what naively we would do is to just say import M1 in M2. Now the definition is there. However, now we are in violation because that FVD and this FVD are different things. So what my tool and my thought process did is that I opted for not doing anything better than just creating a union of the two modules and removing the forward declaration, putting it on the top, and now I have both functions at the same way. Yes?
So I just don't get it. How do we do that if you work on file level?
How I do that if I work on the file level, my module files contain hashmark include statements to the original source code. And then I sometimes remove some lines, but I don't reorganize functions. So what about, yes? Yes, what about module partitions? Now, people came up with the idea of having a same module have multiple sub-translation units which are compiled separately to break up dependency chains. Now, submodules have been thrown out. So partitions is a module internal fluff. They don't change the view of the client. If you say import my module, you will import all necessary interface partitions of it. So, and I admit I didn't know about module partitions when I started working with this. So, but it doesn't fundamentally change the end result. So here's the dependency graph for a particular project. Now we create the flow graph. So using this abstract example, we join together files that depend on each other. Maybe because they include, maybe because they use a symbol from the other one. And then we run a flow cut algorithm, which will say those dependencies you have to. So there's a cycle between modules, which you can no longer have. Previously with includes, you had include guards, but because modules are processes, compiler invocations, you cannot have a cycle between them. So I had to cut the cycles. Here's the example in bigger one. There's a heuristic on which part. So what I do is for each edge, either end of the edge as a file will go into a different module. And first, I only do this for the headers. I split up your project's type system into acyclic list of modules. Here's another example where there are 3 modules involved in a cycle. There's a heuristic on which end of the edge I move, but fundamentally I just put it into another module. So yes?
No, I definitely have a question.
Yes.
I know of no way to automate this. This is something that one has to think about from the inception of a design. And if it has just one little cycle, you might be okay. But if it's just a ball of yarn, there's no
Don't spoil it. Don't spoil it. Yeah. John figured it out. That's the end result. But don't spoil it just yet. We still have half an hour left.
John is thinking about this thing for like 40 years.
So moving implementation to the interface. So we just have this list of dependency modules. We have your type system. Now I know where your files are defined, where your symbols are defined. So because you cannot have a forward declaration in a different module and the definition in another one, not partition, but wholly separate module, I have to move the things together, which I do. But this thing introduces new cycles. Yeah, what about modular partitions? Same answer as above. Yes?
Doesn't the module declaration to go before the import?
Yes.
So what about the export module declaration going before the import? Maybe yes. Clang accepts this. I think Clang accepts it either way. Doesn't fundamentally change the result.
I'm sorry.
Yes?
So just to be sure, and then you modify these header files and put export somewhere, right?
Yes.
Could you repeat the question?
Yes, so I modify the header files by putting exports there. Yes, I put exports on the top level namespaces and exports on the non-namespace symbols.
Like selected one for all of them.
For all of them. I don't know which is a detail in your project because I don't understand the internal one.
Are you using header units or is it just not supported?
No, sorry, what about header units?
Like, header units are actually doing the same without like
No. This is not using header units. This is copy pasting the entire implementation together with it, and then I change the files. I change your files in a subtle way. I don't change their internal structure fundamentally.
Okay, I'm sorry.
Yes.
Another question. Like, if just like the whole preprocessor includes that they would have like the system headers and STL headers there, right?
Yes,
And
system
they
head.
would be like,
No, I don't. So the question is whether or not system headers. Of course, system headers are transitively included here, but I know which files are part of your project, and I'm only touching them.
But your system headers are probably what we call portable headers. So so including system headers will probably get implicitly turned into imports.
well, hopefully, but I'm not sure.
It's implementation defined, but that's something what.
Yeah, somehow it is taken care of. So now, because I moved implementation into the module where the interface is, now I have to take care of the dependencies of just the implementation files, which will include new dependencies on the whole module, which means that there are now, once again, potentially new cycles, which I have to analyze. And then what I opted for, and I don't know of a better automatic solution, is to join them. Yes?
Are those beautiful numbers something that people need to remember?
Attila asked whether or not the names of the modules are something you have to remember. This is arbitrarily generated as a hash because I don't know anything about your project. The idea with this tool was that we run it once on your project, then someone who actually understands the project will refine them. So, but for the algorithm, they are just unique identifiers. I think I hash the names of the files that belong to them. I think that's in the implementation. So I joined the cycles, which means that we have a new module which includes both the files in the original one and unions together the dependencies. So The big test bed for this was Apache Xerxes, the XML parser. That's one of our open source projects, which is the first line of the vanguard on which we test implementations. It has roughly half to half CPP to header ratio. It's very object oriented. And quite frankly, there's not much heavy template magic going on inside Xerxes. There's 38 directories. I didn't use all of them in the modularization. Some of them are platform specific, which I ignored, etc. But of course, just taking an arbitrary project and trying a new approach on it will show that currently working projects are fundamentally broken at some parts.
Really?
Yes, Xerxes as of now works, it compiles, but when I take out this preprocessor and translation unit approach from it, I have seen some very weird mistakes, just small mistakes, yes?
So going back to how you're defining your module files via include.
Here, yes?
Yeah. So that's going to do transit includes. And do you ever put those other includes into other modules?
I think the first, so the question is whether or not transitive includes will break because those files are in other modules. The first part on the broken code slide actually goes into this. Because I know the dependency graph of your project, I know which files I necessarily have to ignore to not break the algorithm. There were cases inside Xerxes, the same header was implemented in multiple files, which fundamentally had to belong to different modules, and I couldn't join them. So there are files I specifically ignored, and I had to work around these includes leaving the module system and then coming back, but it's taken care of inside the algorithm. There's also a case where a header used the macro from the config file of the project, and the header itself did not include the config file, which were not a problem because in the real translation, you need someone before it actually included the config file. People were leaving out forward declarations in headers, and also the header itself didn't include the file that defined the symbol they wanted to forward declare. Once again, you never saw this in a real translation because previous files included them, and people were leaving out header guards too. So these are all mistakes people seem to make and don't realize them, and it's not a problem fundamentally because the project is okay, because the rules in C++, most rules in C++ are defined on the translation unit, not on individual files. So it's still conforming and it still works. So I opted for 14 initial modules, arbitrary decision. I tried different cuts on the project. This seemed to have the nicest looking, completely arbitrary. You just give some initial input to it. After step 3, which is breaking the cycles, I have identified 67 modules. Once again, these are not yet compiling translations. These are just clusters of the type system. This is only on your headers. I have not touched your implementation files yet. And if I didn't handle forward declarations, after joining the files, this is the result I get. The numbers are the number of files belonging to each module. Now, if I do handle the forward declarations, so this is hard to present as it because this was months of trying to put together well-known algorithms and gut ideas to make something work. And once I made a step so it doesn't go into an infinite loop, then it stopped, but then it outputs something the compiler exploded upon. So it was more of an iterative approach of trying to put together a tool. But what happens when I do handle the forward declarations? This happens. OK. This was the moment, I think a few weeks before Christmas. I was preparing for I put the project down because I was preparing some university exams. Big number. And the original number of input files that I did not ignore is 711. So 710 plus 1 is 711. I have to admit this is not what I wished for. I thought maybe 700 files I would have like 300, 100, 200, 150, 150, etc., not this. So what's the actual result? Is that one almost true Unity build, which actually compiles. There are tools for various build systems which create Unity build for you, but they don't take care of all these unification breaker stuff like translation unit local type defs and stuff that break a Unity build if you only just copy paste files together, and there's a lone enum in there. So anyone has a hunch on why? I mean, why didn't this just get merged into the big module?
It was unused.
So the hunch is that it's unused.
That's not my hunch. My hunch is it doesn't depend on anything else.
Yes, John is right. An enum does not have an implementation. It's just an interface, it's just a type. So it doesn't get merged because it's just a type. So this is an example. The enum is PSVI devs. I don't know whatever it means. This was one of the files that used the configuration file for, you know, the macro which create the namespace of the project, whatever, and didn't have the include in it.
It's not
Yes?
that it's just a header file. It's that it doesn't depend on anything else in the system. It depends on things that are not part of the system, so you don't need to merge it in.
Yes, that's right. It doesn't depend. It doesn't depend, and more or less it cannot depend in this case. So I have a one big module which depends on this one, and everything else is in that one big module. Yes?
So checking my understanding here, the process of modularization here was basically for each pair of HPP and CPP, you would then, if my CPP includes other HPPs, I have to merge those also in the same module.
No. For each file, I identified whether or not it's an implementation or an interface, and I replaced header includes, which are part of modules with module import statements. So I had two layers. I was shuffling files around between automatically generated modules and keeping track of what is included and what is imported. And I was shuffling modules around and keeping track of module-to-module dependencies on them. We can discuss the details later, yes?
Okay, I'm not sure it's a proper time to comment, but I think the handling of the forward declaration was covered there. And
Yes.
you probably don't need to just, obviously you can't have forward declaration modules. And what you're doing, you merge the modules. But I think you should do is to extract the class which has a forward declaration in the module.
Yes, the comment is why didn't I extract the class that is forward declared or uses the forward declaration? So forward declaration codependencies. So I don't just merge if there's a forward declaration. I only merge if the module that depends on the forward declaration and the module that gives the definition for the forward declared class depends on the other module that is, so if there's a cycle between the two. So it's kind of a disappointment, okay. But I said there are some performance concerns with modules. Now this is hopefully the right time to track back to it. So in the conventional style, the pre-module style, if I wanted to use something from, let's say, Xerxes, this is just an arbitrary project I used as an example. What I did is I included a header for the type or the class or the function that I wanted to use. I set up the build in a way that it finds the header and it links to the library, and then I used it, right? And I don't know how big XML string is. It's certainly smaller than the whole of Xerxes, which after running this algorithm in any client code, I have to do. All I can do after doing this algorithm, I know it's not called Xerxes in the previous slide. Let's imagine I manually merge that lone enum back into it, is that I say import Xerxes. Then I can use XML string, SAX parser, SAX parser, whatever type is defined in it. Now, and this is an issue if the compiler, if the module is very big and the compiler is taking everything in, like Clang does currently, this is a performance issue. So, and there are bigger things than Xerxes, yes?
And for what I know, all implementations, including Clang, they are not just securely loading the module is just memory mapping it and have a like small like table of things. So it's if this code should be kind of free, assuming you have compiled.
So the comment is whether or not Clang is eagerly loading or just mapping it. Currently, well, I don't know the nitty-gritty inside Clang, but from what I see, the AST, it's called AST Reader. AST Importer is the one that's creating a separate memory for it. AST Reader actually merges it into the translation unit, and with very small checks. Let me go through the rest of the evaluation and the result, and then we can discuss questions, okay? So this is an algorithm or an approach. Every sensible person makes some like evaluation and all the computational theory behind it. So theoretically, it's for all the algorithms that are running inside, it's the number of files to the power of 9 and a whole build. So n to the 9 is a very big number when it comes to algorithms, but the whole thing needed to generate the knowledge, which is of a full build, is measuring it out.
Where does 9 come from?
Flow algorithm is sorry?
Flow is O back to the third plus some.
Yes, and it's a number on the, it has a factor in the edges, and then I calculated like this is the worst case. The worst case is that everyone depends on everyone, and then I have to take one step for each file. This is a very, very eager overestimation, which is calculated out. And so 4-minute build on this machine for Xerxes, and the algorithm in Python took like 30 seconds. So the build is measuring it out. A build, it's more of the fact extraction, but it's comparable to a build. Now, what I did is not touch your existing code fundamentally, which was the original goal. Perhaps it's a very, very blind goal. And the result is that it's not really feasible when it comes to actually making modules. At least I made a good Unity build tool. That's a takeaway. At least I made a good Unity build tool. The key catch is coupling, which creates the dependency, which breaks the thing. And the result is very, very few modules per binary in most cases. However, there was a case I tried running the thing on LLVM itself. It didn't really work because there are certain include flags and whatnot the Python implementation I had did not know about. But the thing is that I found cross-binary modules, which then resulted in linker errors and everything. So it was more of a build system nightmare. People have investigated modules before. Like Manuel in 2016 talked about a different version of modules, which is the header to JSON kind of thing in Clang. In a distributed environment he has at his workplace. And he said that because there was a lot of dependencies going back and forth, the same concept, we have a lot of dependencies which create a Unity build as the result. He said that the only solution here we can think of is to actually make people split up their libraries. This is what Manuel said. Here's the timestamp in the video. You people who are watching, go watch this. It's a very good talk. Now, so I have a result of an algorithm. I don't know. So the algorithm seems to work. I haven't like formally proven it. But the big question is, I have a result. Is that result wrong? Or what if I just made an algorithm and it works well and the result is right? Because when people design their code, they inherently decided on a layout. Okay, this is like a very big image. This is the whole dependency map of Xerxes visualized. You can see there are lines which are thinner and which are thicker. Thicker lines means more dependency on that particular sublibrary. So people decided on their layout. So if my algorithm uses your layout and your code, maybe the fact that it's for this project a Unity build, that's what I can get. Here's a closer example on the thing. So there's a small conclusion left, and then we can talk about, this is generated with Code Compass, and I have no idea why it looks so bad. It looked better I don't know, maybe it's the presenter system I'm using. So we tried, or at least I tried, automatically making stuff, automatically splitting and joining and magicking around your project. But it turns out that if you really truly want to embrace this whole modules thing, there are two things you can do. The first thing is accept the result. Your project is just one big library. Xerxes is the case. Xerxes gets built into one shared object. So having one big unity build for the one shared object in the end is, maybe I should have seen it coming. But then you have a big module, a big size, and then maybe the compiler won't be optimized yet. It will be hard to recompile, etc. Of course, you can use module partitions. And this is more of the fundamental takeaway, is that what I expect in the future is that you will necessarily have to break API because you reorganize stuff, you change your dependencies, and you will spend time and doing refactoring, basically. So, just a summary. We will get to it. Just a summary. I use some papers from other people. So is modules good or bad? Well, it is. I mean, it is a thing. There are good parts, there are bad parts. Hopefully these findings could be, so this tool, what I wish is, hopefully it will be useful for, if not doing modules for you, just showing, because there's like graph visualization and there's a mode for very verbose output, showing the cases, like you have a big project, you don't know where to jump in to change the layout. Now, hopefully, from this output, you can say, this is the one that's very coupled. Here is where you should start thinking about how to redesign it. That will be effort. Build system guys, compiler guys, library developers, clients, standard committee members, people who just put their thoughts up on whatever block possible. Everyone is like, join the ride and hopefully make it happen. I'm not really hoping for the full solution about modularization. And a side note is that the LLVM debugger project started breaking up their project independent of these thoughts I have, of course. And yeah, they decided to just put in work. So maybe in 10 years or 20, we will have modules. And now let's go. You were the first.
So you made the point that you've now got this effective unity built with one huge library you're going to import. You gave me no numbers to say whether actually importing a big library was comparable in expense to the old model of importing the transit to include graph of a header. So did you try any building your test suite with just one import?
Yes, the question is about not giving like numbers behind the size of the import. Now, there are a few, well, I wouldn't say lies. There are a few things that I didn't go into, which are very implementation specific. Parts of, so Xerxes as a module, the part I didn't ignore, compile. But there are a few files which I had to ignore initially, platform-specific stuff, which I couldn't get to compile. Of course, if I put more work into this approach, maybe I could work around the stuff too. So I don't have a full Xerxes. So with this tool, I don't have a full Xerxes that actually compiles. Personal responsibilities and seeing that this is perhaps not going anywhere useful, I stopped tinkering with it. There are a few translation units which are broken because they are not part of the module system, but include into a file which are part of the module system and doesn't have it includes, etc. There were cases with the standard library having no accept, not having no accept, and Clang's like library forward headers or whatever is broken on them. There's a huge fix me on some memory intrinsic function and stuff. So that's why there are no actual tangible measurements on how much it takes to import this particular output. Hopefully there will be, I'm not promising that I will make it, but hopefully there will be a study about how much it costs to templates, like actual measurements on it. Because we have some measurements on preprocessor cost, but that's no longer the big gun in terms of C++.
So in terms of implementation for
Yes.
Clang is totally optimized here. We do lazy loading and do basically hash table lookups for several things. So there is, it's not zero, like a hard zero cost in terms of module size, but it's not linear. It's way better than linear, and it's not even log in, it's way better than log in. So it's very low cost having large modules. The other thing is in terms of complexity of splitting things up for modularization. For Clang style modules, you still have the same problem here of breaking circular dependencies. And so like we've modularized LVM for Clang style modules. And
So sorry, which kind of modules for LVM?
Clang style, but they're just header units. They are,
Oh, so that's the JSON module map thing.
yes.
Okay.
A valid implementation of
Yes.
header units. And at Apple, we've modularized our entire head. That's not all C++ code, but like we have tools to do it. It's not as difficult as being made out to modularize things. It is some work. You have to break cycles.
Yes, I agree that it's, so the comment was about, first of all, Clang being optimized. I did not know about that, but it's, so I worked on Clang specific stuff, but of course the modules is a language feature which perhaps every compiler will do differently. And the other thing is that, of course, it's good. You modularize your stuff. I'm not saying that modularizing a thing is hard. I'm saying that providing a generic solution for modularizing something you do not understand the design of. So doing modularization simply by knowing the language rules and whatever a compiler can tell you about the project, not knowing what PSVI defs means in the context of the particular project, that is what is perhaps hard. Yeah, Bryce was first.
So we do sort of have a legacy story today, which is header units. I mean, you attempted to build a tool to modularize this project, but you could have just made sure that your headers were modular, which is not necessarily non-trivial, and just used header units and use like something like Clang style modules. And I think you would have gotten a lot further with that.
John is shaking his head about
I totally
using.
disagree with what you said.
John was shaking his head about just going over to header units, which is a very nice feature. But how I think of header units, I might be not right, is that they are the feature for the transition phase.
Right, but I think that like a tool that's going to automatically modularize your code is also a tool for the transition phase.
Yes, agree. So John was disagreeing with Bryce. And
Well, my statement is simply that that's not good enough, because just because you don't have a cycle in your header file doesn't mean you don't have a physical cycle in your translation unit, and that's what matters. So it's the union of the headers, the include graph that's taken from the header and the CPP. Assuming you have .h.cpp pairs, we call them components. Assuming that you take the union of those includes, and assuming the includes are sufficient because you don't have forward declares of things that have external linkage, then you can use a very cheap tool to go through and get the envelope of physical dependencies, and it doesn't matter whether it comes from the header or the CPP.
yes, that's why I had to join the cycles in the end and move the implementation and stuff. I ran into actual tangible, like it broke the compilation. Yes.
Yeah, so like it's kind of fortunate that it's just a single module. Have you tried to maybe see how quickly by manually fixing things and breaking cycles you can turn it into like more modules? Like you can take a small subsystem of like sources, how it's called, I think, and like do the right thing to turn it into a module like by hand and see how it improves, like, and run the thing again.
Yeah, yes. The question was about how to turn, like why didn't I just stop the algorithm at a certain point and show the state of it, and then taking a sub part of the library and
like what I was actually trying to ask, does the algorithm help with finding these things you have to do manually, like at higher resolution?
Yes, the algorithm helps to find. I agree, the algorithm is very, very greedy. It's really sensitive on the initial input. That's why I did try Xerxes with different initial inputs, and the end result was the same. So Xerxes is a relatively small library. I don't know, I don't think it's even 20,000 lines of code. And it doesn't use it doesn't use preprocessor magic at all, and it's not using like template metaprogramming and more advanced stuff. The fact that different cuts of the original project also resulted in this collapse, I think that's more of a dim light that shows that either the algorithm is flawed, so either the algorithm and my thoughts are very flawed, which I can agree with, or the algorithm and my thought process proves that upgrading to modules is what I'm saying, it's an effort. So you will have to, as John spoiled the initial surprise during the way, you have to do the redesign. Yes?
So I was wondering, because like I know that for our code base, this would pretty much happen, and that's because like it is roughly layerized, but what we do a lot is with forward declares, we manage to thread, you know, you get a pointer to something that you're not allowed to use here, and then you just thread it through the program and pass it to the same layer somewhere else. And that's a really common pattern, I think, where like that pointer is effectively a void pointer, except it has a type so that it's not a completely void pointer, right? It might as well have been a void pointer because you're not using like that type is included in all of the things, right? Yeah, it's like opaque. It's an opaque handle, right? So if you had an automatic refactor for introduce an opaque handle type and make a separate module up where somewhere, so that you can split the forward declare bit of the module and the not forward declare bit of the module, I think that might actually have yielded something a little better, because people can't physically work without having at least some conceptualization of layering, right?
Well, some people do.
So about the future of putting more cases that is covered by the algorithm. Well, I invited anyone who just wants to tinker about compilers and in Python a bit to try the repository. Personally, I don't think that continuing with this is like viable in a business sense. It's very viable in a personal adventure and for fun, and if you have nothing better to do, but I don't think it's viable in the, like if you have responsibilities and clients and money going on and everything. Sorry, he was first.
Me?
Yes.
Did you consider looking at doing like a min cut on this graph to look at where you would actually be the best place to break cycles?
So I didn't consider a cut on the full graph. I originally created the cycles, I created the graph between the modules, the dependencies, found cycles on them, and then for each individual cycle, I did the cuts. The cycles, so the algorithm is very, very greedy. It's splitting the smallest cycles first. And I don't know at the join phase, like I don't exactly know which implementation I kept about the join phase. I tried, when it has to merge two modules, like when it has to merge multiple modules, it first merges the two biggest ones. It doesn't change if I merge the two smallest ones, because eventually it will all be merged together.
So I have a couple of comments. First of all, when you say min cut, you don't get the same weight on a dependency. A direct dependency might be easy to break or hard to break. If you have 10 easy-to-break dependencies or one hard-to-break dependency, who knows? Anyway, that doesn't work. Just simply doesn't work. You have to design things up front so that they don't have the cycles. There are levelization techniques where you can cheat, and you can make it look like it isn't dependent, but architecturally, it's still just as cyclic. It's just that you've cheated and you have to do some stuff upstairs to arrange for the connectivity at a higher level. But that's another story. The worst problem is that even if you had all of this, even if you had wonderful infinite cost, you could refactor your library and make it perfect, you have a whole bunch of clients that are using your library that will then...
We don't have time for a live demo on camera. I will do it afterwards. Yeah, so we are kind of out of time. So one last question from Bryce.
It's more of a comment. We have a whole study group on the committee exploring these issues. SU15, the one group, I chair it. There's actually a telecon that's going on right now, an SU15 telecon, which I'm not chairing, but we have them like every 2 weeks. You should call in and chat with us.
All right. I will look into the mailing lists. I don't really like. I'm not from the United States, and due to time zones might be an issue, and I don't really know all these connections. But hopefully, this was the rightest moment to make those connections. So yeah, so I think the remainder should be in the break. So thank you for coming.